So in this lesson, we're going to go ahead and continue our study of the integers modulo n, but now we're going to start going into their properties of addition and multiplication. And the goal for this lesson is to prove that the integers modulo n forms a ring. In other words, those axioms that we covered in our first lesson for the integers are also satisfied for the integers modulo n. And when I mean axioms, the axioms to be a ring. I'm not referring to the inequality since that won't hold, but the axioms for a ring, specifically we have associativity, commutativity for addition, we have an additive inverse, and we have a zero under addition, and in multiplication we have a 1. And so those properties will show that they hold on for the integers modulo n. Some of them I'll be leaving for homework, but we're going to go through most of the coverage. So when we talk about the integers modulo n, as a reminder, we're looking at the set of congruence classes, or in the language of structures, the set of equivalence classes under the relation modulo n. So if we fix a natural number n, we look at the integers modulo n, we're denoting it by this notation, c sub n, and that will just be the collection because of the fact that 0, 1, 2, all the way to n minus 1 is a complete set of representatives. We can go ahead and say that the whole set is 0 bar, 1 bar, all the way to n minus 1 quantity bar. The set of equivalence classes, or congruence classes as the book calls them, is a bar, where this is the set of a plus kn, where k is an integer, and we define addition and multiplication as a bar plus b bar equals a bar plus b, and then that whole thing bar, and a bar plus b bar is a times b quantity bar. And so that's what we're going to be defining it. As a concrete example, let's look at 4. We know, actually, let's look at 5. So let's look at 5. We know that 5 is congruent to 2 mod 3. And so we have that 5 bar is equal to 2 bar in the integers modulo 5. If we add 2 plus 5, we get 7. Modulo 3, we have that this is 1. So what this is getting at is that we do 2 plus 5 bar, that this will be the same as 1 bar. But that's just coming from how we define it. 2 plus 5 is 7. 7 is congruent to 1 mod 3. And therefore, we have that this is going to equal 1 bar. And so working under these congruence classes is a nice way of being lazy, because we're working with modular arithmetic language, but we don't have to write mod n at each step, and so it makes it a much neater notation. But we can also define multiplication tables just as we did when we were first learning arithmetic and adding and multiplication in our earlier schooling. So for example, let's look at the integers modulo 3 under addition. So we have 0, we have 1, we have 2, but 3 is 0, so we're going to 0 bar, 1 bar, 2 bar, and then 0 bar, 1 bar, 2 bar. 0 plus 0 will be 0. And I'm going to use notation. I'm not going to write the bar, and this is very common. When you're working in the integers modulo n, and the n is known from context, it's often the case that one abuses notation and omits the bar. And so you'll notice this in the textbook, and I'm going to also adhere to this convention at times in the notes. When I write 0 here, there is an implicit assumption that this 0 is not the 0 of the natural numbers, but the 0 in the set of the integers modulo n, so specifically 0 bar. And so I'm not writing that bar, but it's understood from context that this is really a congruence class. If we do 0 plus 1, we get 1. If we do 0 plus 2, we get 2. If we do 1 plus 1, we get 2. If we do 1 plus 2, we get 3, which is 0. And if we do 2 plus 1, we're going to get 0. And if we do 2 plus 2, we get 4. But 4 is congruent to 1 mod 3, so we get 1. And so we have a addition table. In the same manner, we can do one for multiplication. Zero times 0, 0. Well, everything by 0 will be 0, so we have this. And we can do 1 times 1, we get 1. 1 times 2. And then finally 2 times 2 is 4, but 4 is 1. And so we have our multiplication table for the integers modulo 3. And so this is what we have just done. So in observation, we see that 1 and 2 are additive inverses of each other, because if we do 1 plus 2, 1 plus 2, we get 0. If we do 2 plus 1, we get 0. And so we have that 1 and 2 are additive inverses of each other. In the same manner, we have that if x times y is equal to 0 bar, then x or y must be 0. Let's see. If we look at all the cases where we have 0, so over here we're being multiplied by 0, and over here we're being multiplied by 0. The non-zero entries, this lower right square, correspond to things that are non-zero when we multiply them. And by non-zero, since we're working in the integers modulo 3, we're talking multiples of 3. So whenever we in other words, whenever we multiply numbers that are not divisible by 3, we're going to get non-zero values back. And so we have, or in the case of the integers modulo 3, that the zero theorem will hold. We're going to prove that later, but we see that if xy equals 0 bar, then x or y must be 0. And so that raises a question. When working in the integers modulo n, does the zero theorem hold? So, question. In the integers modulo n, is it the case that x times y equals 0 bar imply that x is equal to 0 bar or y is equal to 0 bar? So here's a question I want you to think about. And go ahead. I ask that at this point you pause the video and work out what happens in the integers modulo 6 and see if this happens. So go ahead and pause the video and work it out. Please work it out, and when you unpause, I will go ahead and give a response to this. So now that you have worked on the integers modulo 6, we can see that if we look at 2 bar and in 3 bar, this is going to be 6 bar. But in the integers modulo 6, this is 0. But of course, 2 is not equal to 0. And 3 does not equal to 0. And so this is one property that is not satisfied from the integers modulo n when we compare them to the integers. In the integers, we have the zero theorem at our disposal, but we don't necessarily have a zero theorem in the integers modulo n. We will show later that if p is prime, then we do. And so that's something that we will be showing later on. So I just want to point that out. So let's continue. So just an observation. So we were looking at the zero theorem in the case of primes, and I mentioned that we're going to show it for this. We're going to show this result more generally when p is prime, that the zero theorem holds. But what we will actually see in the process is that we really are just looking at Euclid's lemma in disguise. Because what does it mean when we have n times m is congruent to 0 mod 3? That means that n times m is divisible by 3. But because 3 is prime, Euclid's lemma asserts that 3 must divide n, or 3 divides m. And so the zero theorem is Euclid's lemma when p is prime. And so that's something we're going to come back to later on. Another thing I want to point out that distinguishes the integers modulo n from the integers themselves is the notion of having a multiplicative inverse. So for example, we could ask the following question. If n is in z, does there exist a m in z such that n times m is equal to 1? And the answer here is, well, only if n and m are 1 themselves. Because what happens if we have 2? For this to be true, if 2 times m is equal to 1, then m must be 1/2. That's not an integer. So only if the absolute value of n is equal to 1. Only true. And so that's what we have here. But that's something that is not, this property that in the integers it has to be plus or minus 1. When we look at the integers modulo 3, we see something that we wouldn't expect over the integers. Specifically, we can see that 2 times 2 gives us 1. So in other words, 2 is a multiplicative inverse of 2. Very different than the setting of the integers where we would need to have, we will need to go to the realm of the rational numbers to be able to cancel off the 2 to get back to 1. Here we can. And so this is another property that we're going to be exploring further in our investigation of the integers modulo n. Now, in the same manner, we can go ahead and consider the multiplication table for the integers modulo 4. And I've gone ahead and added it here. We can go 0 plus all the elements, which just be 1, 2, 3, and the same thing here, symmetric. And then all of this will be symmetric along this diagonal because of commutativity. Same thing on the multiplication side. And so we can see that 2 plus 2 will be 4, so we have 0. 3 plus 3 will be 6, but we're doing it modulo 4, so we get 2. 3 times 3 is 9, but 9, when we divide it by 4, has remainder 1, so we get back 1. 2 times 2 is 4, so we get 0 there, as we saw in the last slide. And so a consequence is that now we see that 1 and 3, when we add them, we get back 0. And so they're additive inverses of each other. And 2 is its own additive inverse, because if we do 2 plus 2, we get 0. But now, in the same way that the example that I asked you to look into, we don't have the zero theorem holds for 4. Because if we look at this here, we have a 0 here that is 2 times 2. But 2 is non-zero modulo 4. It's just 2. And so here we have 2 non-zero numbers in the integers modulo 4 multiplying to 0. And this is going to be something that we're going to be seeing whenever we have the integers modulo a composite number. The theorem does not hold. But one of the good things that we will be showing later on in the course is that we will be able to prove precisely when we have multiplicative inverses. Because 2 doesn't have a multiplicative inverse. But we see that in the case of 3, let me switch the color. So in the case of 3 times 3 is 1. So 3 is its own multiplicative inverse. Same thing with 1, but that's cheating. And so we do have multiplicative inverses that don't satisfy the property that in the integers where it has to be the absolute value of 1. So even though we have a failure of a multiplicative inverse property at 2, we're still okay with 3. And what we will be showing is that we have multiplicative inverses precisely when the numbers that the number we are considering is relatively prime to the modulus. So in this case, we're reducing modulo 4. 4 is our modulus. And 3 is relatively prime to 4. And so we should expect that it has a multiplicative inverse, and we will be proving that statement later in the course. And so this is just sort of alluding to things that we are going to be investigating further in the future lessons. And also, for homework, you'll be doing some of these multiplication tables. And so these are patterns I ask that you be in the lookout as you're working through these things. Don't work through them mindlessly, but study their structure. What are the patterns that you observe? What happens when we're looking at a modulo a prime versus modulo a composite number? I'll also mention that on page 307 of the textbook, you will find a multiplication table for the integers modulo 6, and so that is available for you. And so with that, let's go ahead and extend the main theorem from the last lesson. So in the last lesson, we proved conditions for being equivalent under congruence modulo n. Specifically, we showed that 1, 2, 3, and 4 were equivalent. Now let's go ahead and extend this. Let's consider the case of a bar equals b bar in the integers modulo n. Well, the proof will follow automatically from theorem 161 and the definitions. So by theorem 161, 1, 2, 3, 4 are logically equivalent. So it suffices to show that 5 is equivalent to any of the statements 1, 2, 3, or 4, and we're going to show that it's equivalent to 1. So let's go ahead. Suppose that A is congruent to B mod n. So this is equivalent by the theorem to A is equal to B plus nk for some integer k. By definition of Zn, so actually by definition, technically the theorem on equivalence classes, by our theorem on the integers modulo on congruence mod n being an equivalence relation, we have that A bar is the set of elements of the form, let me do B bar, B plus nk, where k is now ranging through any integers. So to not abuse notation, I'm going to switch this to an L, since we already have k appearing in A, where now A and B are fixed, so that fixes k. So let's say that this is L instead of k. In particular, A is in B bar. And thus, A bar is equal to B bar, since that is an equivalence relation. So there we can go ahead and choose A as a representative, and the equivalence class of A is the same as B bar. And that's our notation for congruence classes in integers modulo n. And so now we go backwards, and this whole process is reversible, because if we have A bar is equal to B bar, that means that A is in B bar, which in turn tells us that A is in this set here, which is how we define B bar. And so all of this is reversible. So we could have replaced this in particular to this is equivalent to and so now all of these things are equivalences, and so we now trace our way backwards, and we get that A bar equals B bar is the same as A congruent to B mod n. And so now that establishes theorem 171. And so now we have our statement for the various equivalent statements for congruence. And one thing that actually happens in terms of definitions in mathematics, oftentimes in earlier courses, and depending where you are in terms of math courses you have taken, oftentimes one first states a definition and then goes on and uses the definition. From a rigorous standpoint, the reality is that it's actually backwards. behind every definition, there is a statement of the following are equivalent. And you define then if this thing satisfies any of the properties that were in that statement, then that's what we defined as. So when we think about congruences, the reason I'm bringing this up is that you want to think about a congruence as being any of these 5 statements since they are equivalent. So whenever we say A is congruent to B mod n, it really is the same as saying A bar equals B bar in the integers modulo n. And so when I use the word congruence, it really means any of these 5 statements. And that's really common as you go through upper level math books. You'll start to see more of a theorem, the following are equivalent, followed by a definition that says we say that something is blah if any of the above properties are satisfied, where the above properties refers to the various statements appearing in the following are equivalent, as we see here. And so that's just a little side note in terms of definitions, that the definitions really invoke an equivalent statement of various statements. So to continue in line with this notion of equivalences between congruence, A congruent to B mod n, and now the new notation in the integers modulo n, let's look at proposition 1.7.2, which is a restatement of theorem 165 when applied under the equivalent conditions we are now investigating. So for example, for the proof of 1, just going to go ahead and just briefly go through this, which is just 165 being reinterpreted. We have A bar is equal to X bar, B bar is equal to Y bar. Both of these statements by the previous theorem, and let me just get the label. This is 824 from the book. By theorem 824, this is the same as A congruent to X mod n, B congruent to Y mod n. And so now we have that by theorem 721, which is up here, the one that we proved in the last lesson. So now theorem 165 implies that A plus B is congruent to X plus Y mod n, which by another replication of theorem 8.2.4 tells us that A plus B bar is equal to X plus Y bar. And so we have statement 1 in this fashion. And then statement 2 follows a similar argument because we can just go, I'm not going to label the statements for the theorems, but the same argument. We go from this statement here, and then we get AB congruent to XY mod n, and then 824 tells us that now AB is equal to XY, and so we have the statement of the proposition. And so all that we have done is use theorem 165, or it's theorem 721 specifically to use the book notation. We use that theorem in conjunction with the equivalence conditions for being congruent, and all we have done is just do a translation. And so what I want to emphasize, what we are doing now is just translating the statements from the last lesson where everything was in terms of modulo n to this congruence notation that allows us to be lazy, because now we don't have to write mod n, we just go ahead and use the bar notation. And that's really what we're doing right now, it's just using this bar notation, and then that simplifies our writing. So now we're ready for our main theorem. The integers modulo n is a ring. And so, as a reminder, when we say that a set is a ring, we're in this case the integers modulo n, we're saying that the set of the integers modulo n, together with the operations of addition and multiplication, has the following axioms being satisfied: associativity, commutativity, identity, additive inverses, associativity, commutativity, the identity, and distribution And we saw this in the case of the integers, we took this for granted. But this time around, we can actually go ahead and prove it by relying on the fact that the integers is a ring. So I'm not going to do all of these. So I'm going to leave for you to work out the following cases. So commutativity, associativity for multiplication, commutativity for multiplication, and the distributive property. So let's focus on the ones that are remaining. So for the proof, this is how we're going to go ahead and argue it. Let A bar, B bar, C bar be elements in the integers modulo n. Because we're choosing these congruence classes, then we have that A, B, and C we can take to be integers. These are the representatives for those congruence classes. And so we have this. Now, if we consider by the axioms of Z, so specifically since the integers, actually let me label this A1, so I'm going to go ahead, so let's verify associativity for addition. So since Z is a ring, we have that A plus B, parentheses, plus C, is the same as A plus B plus C. Now, when we come down to congruences, we know that these properties are still satisfied. So then, A plus B bar plus C bar is equal to A bar plus B plus C bar. Since that is that we have defined addition modulo n. And so now this shows A1. And so we are done. And so we have proven associativity by relying on the property that the integers are associative. This is reminiscent of linear algebra. If you took linear algebra with a focus on vector spaces, when proving that other things are vector spaces, oftentimes you relied on the fact that the real numbers is a vector space to get your conclusion. And that's exactly what we're doing here. Since we have that the integers is a ring, we can go ahead and then translate everything, work with the integers to get our statement about the integers modulo n. So let us go ahead and now show A3. So this is identity in Zn. We're going to do it the same way. So since Z is a ring, zero is the additive identity. And thus, A plus 0 is equal to A, which is equal to 0 plus A for any integer in Z. But then this equation implies that A bar plus 0 bar is equal to A bar plus 0 bar plus A bar for every single congruence class in the integers modulo n, which establishes the existence of an additive identity in the integers modulo n. And once again, we have done it by adhering to the properties in Z. Similarly, we can go to A4, use the same property. We go again, since Z is an integer, there exists an additive inverse minus A for A in Z, such that A plus minus A is equal to 0. Now, if we go ahead and reduce modulo n, we get A bar plus minus A bar is equal to 0 bar, which establishes that minus A bar the congruence class of negative a is the additive inverse of a bar. And so we have that additive inverse also holds. So I'm going to go ahead and shrink this. So next we're going to do the multiplicative identity. And in the same manner, we rely on the fact that 1 is a multiplicative identity for the integers. So since 1 is the multiplicative identity of z, we have that x times 1, that a times 1, is equal to a for every integer a and z. And now reducing that modulo n, we have a bar times 1 bar is equal to a bar for every congruence class in the integers modulo n. And that establishes the statements that we were going to prove. And so for the remaining ones, commutativity, associativity, commutativity, distributivity, you can go ahead and prove that those also hold by adhering to the same argument. First start with the fact that it holds over the integers, reduce modulo n, and you get your proof. So let's go ahead and now do some examples. So I'm going to do the following two exercises from the text. So A213 and A215. So we're going to do first A213. And so what this says is if a, x, and y, all of those congruent classes in the integers modulo n, then a bar plus x bar is equal to a bar plus y bar, then x bar equals y bar. And so let's go at this from only using the fact that the integers modulo n is a ring. So first thing is, since the integers modulo n is a ring by the previous theorem, minus a bar is the additive inverse of a bar. And therefore, if we now go through the equation and do the properties of addition that we're used to, so now we have, therefore, we do a bar plus x bar is equal to a bar plus y bar. This is a ring, and that's the key thing. Now that we have established that it's a ring, we don't have to go to the integers first and then do the statement in the integers and then prove it. We can now just work in the realm of the integers modulo n. So I'm not going to the integers to make the argument, even though we could. We can now use the fact that it's a ring. We have additive inverses, so we can now add both sides by the additive inverse of a. So I'm going to just put it over here, add by minus a bar on both sides. But the fact that a bar plus minus a bar is equal to 0 then tells us that this here is just going to be x bar plus 0 bar is equal to y bar plus 0 bar. And technically, I skipped a step. If you take when you take abstract algebra, if you have taken abstract algebra, one of the things that's drilled into you is that you do want to use the axioms, especially if you have something that is non-commutative. So technically, we want to go ahead and first do this as a bar plus minus a bar plus x bar. And so here we're using the fact that it's commutative. By commutativity of addition. And so we have done this. And now we use the fact that a bar plus negative a bar is 0 bar. Since we're looking at the additive inverse of A. So we have this. But then 0 is the additive identity. So we get x bar equals y bar, since 0 bar is the additive identity. And we are done. We have now proven A2 13. So let's go ahead and do the next one. And so for A2 8.2.15, we now go about it in the same way, but now use the multiplicative properties. So we're going to go ahead and do the following. We're just going to go ahead and expand. So by properties of addition and multiplication, in the end, we have the following. We have that A bar plus B bar squared is the same as A bar plus B bar times A bar plus B bar. But now we have the distributive property at hand. So we have that we can distribute. And this here, that will boil down to foiling. And so we'll have A bar times A bar plus A bar times B bar plus B bar times A bar plus B bar squared. And of course, I'm going through all the motions, but the key thing is we really are just doing the same thing we would do over the integers or polynomials. All these things behave because it's a ring, and that's the key. It's a ring, so all the properties that we are used to hold. And so we have here A bar squared, AB plus and then BA. By commutativity, that's A bar, B bar. The nice thing about being in a commutative ring, there are non-commutative rings, and in those types of rings, we wouldn't be able to do this. But because everything is nice, we can. And so we get twice A bar, B bar, and then technically that's 2 bar, plus B bar squared, which is what we wanted to prove, and now we are done. And so that concludes this exercise. And so this lesson is going to be on the short end, and that's intentional. What I want to emphasize as we go into this properties of addition, multiplication, and the fact that the integers modulo n is a ring, is that you have time to work on the homework assignments and get familiar with these notions and properties, since we're going to be using them extensively. And so for that reason, I'm going to end this lesson here. And once we have gotten comfortable with this terminology and language, we're going to then go ahead and now start proving results that modular arithmetic allows us to prove nicely without that much work. And that will be the context of the next video, where we're going to be investigating multiplicative inverses and more properties of the integers modulo n.